Welcome to our deep dive into demodulation in communication systems. In this video, we'll explore what demodulation is, why it's essential, and how it fits into the broader context of modern communications. Whether you're a student, an engineer, or just curious about how your phone or radio works, understanding demodulation is a key step. We'll start by defining demodulation, then move on to its role in extracting information from signal. Let's begin our journey by setting the stage for why demodulation matters in today's connected world. Modulation is the process of recovering the original information-bearing signal from a modulated carrier wave. In simple terms, when information like voice, data, or video is transmitted over long distances, it's often combined with a carrier signal through modulation. At the receiving end, demodulation is used to separate the original message from the carrier. This process is fundamental to all communication systems, from radios to smartphones, ensuring that the transmitted information is accurately received and understood. Imagine trying to listen to a song on the radio without demodulation. The music would be buried within a high-frequency signal, making it impossible to hear. Demodulation is crucial because it extracts the meaningful content from the modulated carrier, allowing us to enjoy clear audio, view crisp images, or receive accurate data. Without demodulation, all the information sent over communication channels would remain inaccessible, making modern communication as we know it impossible. Any communication system, modulation and demodulation work hand in hand. Modulation prepares the signal for transmission by combining it with a carrier wave, making it suitable for travel over various media. At the receiving end, demodulation reverses this process, retrieving the original information. This cycle ensures that data can be sent efficiently over long distances and then accurately recovered. Understanding both sides of this cycle is vital for grasping how communication systems operate. Before diving deeper into demodulation, it's important to understand the types of modulation used in communication systems. The most common types are amplitude modulation, AM, frequency modulation, FM, and phase modulation, PM. Each type modifies a different property of the carrier wave to encode information. The choice of modulation affects how demodulation is performed at the receiver, as each requires a specific technique to extract the original signal. Amplitude modulation, or AM, is one of the earliest and simplest forms of modulation. In AM, the amplitude of the carrier wave is varied in proportion to the information signal. This method is widely used in radio broadcasting. Demodulating an AM signal involves detecting these amplitude changes and reconstructing the original audio or data. The simplicity of AM makes it easy to implement, but it's more susceptible to noise compared to other methods. Frequency modulation, or FM, changes the frequency of the carrier wave according to the information signal. FM is popular in high-fidelity radio broadcasting because it offers better noise immunity than AM. Demodulating FM signals requires a different approach, focusing on detecting frequency variations rather than amplitude. This makes FM ideal for applications where signal quality is critical, such as music and voice transmission. Phase modulation, or PM, involves changing the phase of the carrier wave to encode information. While less common in everyday broadcasting, PM is widely used in digital communication systems. Demodulating a PM signal requires detecting phase shifts and translating them back into the original data. PM is often used in combination with other techniques to achieve robust and efficient communication, especially in wireless and satellite systems. Now that we've covered the main types of modulation, let's look at the corresponding demodulation techniques. Each modulation type requires a specific demodulator to recover the original information. For example, AM signals use envelope detectors, FM signals use frequency discriminators, and PM signals use phase detectors. Understanding these techniques is crucial for designing and troubleshooting communication systems. Envelope detector is a simple and widely used demodulator for AM signals. It works by tracking the peaks of the modulated wave, effectively following the envelope that represents the original information. Envelope detectors are easy to build and are commonly found in AM radios. However, they work best when the signal is strong and relatively free from distortion or noise. Synchronous detector is a more advanced demodulator for AM signals. Unlike the envelope detector, it uses a reference signal synchronized with the carrier to extract the original information. This method provides better performance in the presence of noise and distortion, making it suitable for high-quality audio applications. Synchronous detection is more complex but offers improved fidelity and reliability. For FM signals, the frequency discriminator is a common demodulator. It converts frequency variations in the received signal into amplitude variations, which can then be processed to recover the original information. Frequency discriminators are essential for FM radios, providing clear and noise-resistant audio. They are a key component in ensuring the high quality of FM broadcasts. Phase detectors are used to demodulate PM signals. They work by comparing the phase of the received signal with a reference signal, allowing the original information to be extracted. Phase detectors are crucial in digital communication systems, where phase modulation is often used for efficient data transmission. Their precision ensures accurate recovery of information, even in complex communication environments. Modulation techniques can be broadly classified as coherent or non-coherent. Coherent demodulation requires a reference signal that is synchronized with the carrier, offering higher accuracy and better noise performance. Non-coherent demodulation, on the other hand, does not require synchronization, making it simpler but sometimes less effective in noisy environments. The choice between these methods depends on the application and desired performance. With the rise of digital communication, digital demodulation techniques have become increasingly important. These methods are used to recover digital data from modulated signals, such as those used in Wi-Fi, cellular networks, and satellite communications. Digital demodulation often involves more complex algorithms and signal processing, but it enables high-speed, reliable data transmission across the globe. Amplitude shift keying ASK is a digital modulation technique where the amplitude of the carrier is varied to represent binary data. Demodulating ASK signals involves detecting these amplitude changes and converting them back into digital bits. ASK is simple to implement but can be sensitive to noise, making it suitable for short-distance or low-noise environments. Frequency shift keying, FSK, uses different frequencies to represent binary data. Demodulating FSK signals requires distinguishing between these frequencies and mapping them back to digital values. FSK is widely used in applications like modems and wireless communication, offering better noise immunity than ASK. Its reliability makes it a popular choice for many digital communication systems. A-shift keying, PSK, encodes data by changing the phase of the carrier wave. Demodulating PSK signals involves detecting these phase changes and reconstructing the original digital data. PSK is highly efficient and robust, making it ideal for high-speed data transmission in wireless and satellite systems. Its effectiveness in noisy environments has made it a cornerstone of modern digital communication. Quadrature demodulation is a technique used for signals that have both in-phase, I, and quadrature Q components, such as in quadrature amplitude modulation QAM. This method separates the signal into its I and Q parts, allowing for the recovery of complex data streams. Quadrature demodulation is essential in modern digital communication systems, supporting high data rates and efficient spectrum usage. With advances in computing, software-defined demodulation has become increasingly popular. Instead of relying solely on hardware, these systems use software algorithms to demodulate signals. This approach offers flexibility, allowing updates and improvements without changing physical components. Software-defined demodulation is widely used in modern radios, communication devices, and research applications. Wireless communication systems, such as cellular networks and Wi-Fi, rely heavily on demodulation to deliver clear and reliable data. These systems often use advanced digital modulation and demodulation techniques to maximize bandwidth and minimize errors. The ability to accurately demodulate signals is critical for maintaining high-speed, uninterrupted wireless communication. Satellite communication systems use sophisticated demodulation techniques to handle signals transmitted over vast distances. These systems must compensate for signal delays, noise, and interference. Advanced demodulators ensure that data sent from satellites is accurately received on Earth, supporting everything from GPS navigation to global broadcasting. Optical communication such as fiber optics also relies on demodulation. Here, light waves are modulated to carry information, and specialized demodulators recover the data at the receiving end. Optical demodulation enables high-speed internet, long-distance phone calls, and data centers to function efficiently, forming the backbone of modern digital infrastructure. Radio broadcasting is one of the most familiar applications of demodulation. Whether it's AM or FM radio, demodulators in your receiver extract the audio content from the transmitted signal. This process allows millions of people to enjoy music, news, and entertainment every day, demonstrating the practical importance of demodulation in daily life. Television broadcasting also relies on demodulation to deliver both audio and video content. Modern digital TV systems use advanced demodulators to handle complex signals, ensuring high-definition images and clear sound. The evolution of TV technology has been closely tied to improvements in demodulation techniques, allowing for better quality and more channels. Every time you make a call or send a message on your mobile phone, demodulation is at work behind the scenes. Mobile networks use a variety of modulation and demodulation techniques to transmit voice, text, and data. The efficiency and reliability of these processes are key to the seamless communication we enjoy on our devices. Internet relies on demodulation at multiple stages, from your home modem to massive data centers. Modems, short for Modulator-Demodulator, convert digital data into signals suitable for transmission and then demodulate incoming signals back into usable data. This process is essential for web browsing, streaming, and online communication. Internet of Things, IoT devices from smart thermostats to wearable fitness trackers depend on demodulation to communicate. These devices often use low-power, efficient modulation and demodulation schemes to send and receive data. Reliable demodulation ensures that IoT devices can operate seamlessly, sharing information and responding to commands in real time. Many modern medical devices, such as wireless heart monitors and telemedicine equipment, rely on demodulation to transmit patient data securely and accurately. These systems use robust demodulation techniques to ensure that critical health information is delivered without errors, supporting timely diagnosis and treatment. Modern vehicles use communication systems for everything from GPS navigation to wireless key fobs. Demodulation plays a key role in these systems, enabling reliable data transfer between sensors, controllers, and external networks. As cars become more connected and autonomous, advanced demodulation techniques are increasingly important for safety and performance. Industrial automation systems use demodulation to facilitate communication between machines, sensors, and control systems. Reliable demodulation ensures that commands and data are transmitted accurately, supporting efficient and safe operation in factories and industrial plants. As automation advances, the demand for robust demodulation solutions continues to grow. Security systems, such as wireless alarms and surveillance cameras, depend on demodulation to transmit and receive signals. These systems require secure and reliable communication to function effectively. Advanced demodulation techniques help prevent interference and ensure that security alerts and video feeds are delivered without delay. Broadcasting, whether radio, television, or digital streaming, relies on demodulation to deliver content to audiences. Demodulators and receivers extract the transmitted information, making it possible for us to access news, entertainment, and educational programs from anywhere in the world. The evolution of broadcasting technology has been driven by advances in demodulation. Navigation systems, such as GPS, rely on demodulation to interpret signals from satellites. Accurate demodulation is essential for determining position, speed, and direction. These systems enable everything from smartphone navigation to aircraft and maritime guidance, highlighting the critical role of demodulation in transportation. Military communication systems use advanced demodulation techniques to ensure secure and reliable transmission of information. These systems must operate in challenging environments with potential interference and jamming. Robust demodulation is vital for mission-critical operations, supporting everything from encrypted voice communication to data links for drones and vehicles. Space missions rely on demodulation to receive data from spacecraft and satellites millions of kilometers away. These signals are often weak and subject to interference, requiring highly sensitive and precise demodulators. The success of space exploration, from Mars rovers to deep space probes, depends on the ability to accurately demodulate signals across vast distances. Demodulation is not without its challenges. Noise, interference, and signal distortion can all affect the accuracy of demodulation. Engineers must design systems that can handle these issues, using advanced filtering, error correction, and adaptive techniques. Overcoming these challenges is essential for maintaining reliable communication in all environments. Error correction techniques are often used alongside demodulation to improve reliability. These methods detect and correct errors that may occur during transmission, ensuring that the recovered information is accurate. Error correction is especially important in digital communication, where even small errors can have significant consequences. Adaptive demodulation systems can adjust their parameters in real time to cope with changing signal conditions. This flexibility allows them to maintain optimal performance even in challenging environments, such as mobile or wireless networks. Adaptive demodulation is a key feature in modern communication systems, supporting robust and efficient data transfer. Choice of demodulation technique can impact the bandwidth efficiency of a communication system. Some methods allow more data to be transmitted in the same bandwidth, while others prioritize reliability or simplicity. Balancing these factors is a critical part of communication system design, ensuring that users get the best possible performance. Latency or delay is another important consideration in demodulation. Some techniques introduce more delay than others, which can impact real-time applications like voice calls or live streaming. Engineers must choose demodulation methods that minimize latency while still providing reliable data recovery, especially in time-sensitive systems. The field of demodulation is constantly evolving, with new techniques emerging to meet the demands of faster, more reliable communication. Advances in digital signal processing, machine learning, and artificial intelligence are opening up new possibilities for adaptive and intelligent demodulation. These innovations promise to make communication systems even more efficient and robust in the years to come. 5G networks use advanced demodulation techniques to support ultra-fast data rates and low latency. These systems must handle complex modulation schemes and rapidly changing signal conditions. The success of 5G depends on the ability to demodulate signals accurately and efficiently, enabling new applications like autonomous vehicles and smart cities. Researchers are continually developing new demodulation algorithms to push the boundaries of communication technology. These efforts aim to improve efficiency, reduce errors, and enable new forms of communication. The ongoing research in demodulation is vital for the advancement of everything from consumer electronics to space exploration. Summary: demodulation is a cornerstone of modern communication systems, enabling the extraction of valuable information from modulated signals. From radio and television to the internet and beyond, demodulation makes it possible for us to connect, share, and innovate. As technology advances, the importance of efficient and reliable demodulation will only continue to grow, shaping the future of global communication.